Okay, so what is estimation in the first place? In statistical inference, estimation is a vital process that involves using sample data to estimate or predict population parameters such as the population mean and variance. So we mentioned the term parameters. So specifically the parameters, these are measures used to describe the population. Okay. Common examples of parameters are the population mean and the variance. But if we are talking about the sample, then the term parameters could be quite technically inaccurate or technically wrong. Okay. Technically we call that statistics. Okay. So if the population mean and population variance are parameters, then the statistics are the sample mean and the sample variance. Or those are the common examples. Okay. So now um normally we our focus here for this course are most of the things that we're going to talk about are assuming our data is normal, okay, or our data set has a normal distribution. Okay, when we say normal distribution, when you plot their probability of all the possible values to happen, they will form a Gaussian curve like this, bell curve. Okay, so symmetrical, smooth bell curve. Okay, so in this curve, the centermost or the top, as you can see, the centermost portion is the highest or the peak. Okay, that's actually the part where we assume the true population mean. Okay, so because technically speaking, it has in or mathematically speaking, this portion of the curve has the highest um area of a strip. Okay, that's in calculus. So, or in short, if the height represents the probability value of any point in this curve, then the point that has the highest probability value is the centermost portion, and that is if your data is normal. All right. So in most cases, the population mean is unknown, and we are just trying to estimate it. Okay, so that's what estimation is all about. We do that by taking a sample from the population to estimate the population mean, and we have two main options on how we do that. Either we consider a point estimate or an interval estimate. So point estimate, we are talking about a specific value. Okay, while interval estimate, we are talking about a certain range. Okay, so for this course, our focus is more on point estimates. Okay, so let's see. Point when we are considering only point estimates, then we are doing actually point estimation, which is a part of the estimation component of statistical inference that involves using sample data to estimate an unknown population parameter, such as the mean, population mean, or the population proportion, or even the variance. Um, and what we need to be is to be an unbiased estimator. Unbiased. So an estimator is said to be unbiased if on average it produces estimates that are equal to the true parameter value, meaning the expected value of the estimator is equal to the parameter it is trying to estimate. Okay, so we're going to see that later. How do we do that? Or for now, just remember that we can be an unbiased estimator if we are handling only normal distribution. Or should we say, if the data that we are handling is normal. Okay, so if you push something, you try to do these estimates, even if you know your data doesn't have a normal distribution or has far from normal distribution, then you are now a biased estimator. Okay? So take note that an unbiased estimator is desirable because it minimizes systematic errors in the estimation process. Okay, so in estimation, of course, we cannot be exact at all times. There could be some errors or differences between our target value and our estimated value. Okay, so we have such things as errors, such as the standard error or SE. It is an estimate of the standard deviation of a sampling distribution. And we can compute that by dividing our sample standard deviation, by the square root of our sample size. Okay, so another thing, we have the MSE or the mean squared error, which is a measure of its accuracy. Basically, the MSE is our variance. So sample variance, once we have our sample variance, just square it, or that would mean, um, okay, um, right? So if you have your sample standard deviation, you're looking for SE, just divide it by square root of the sample size. But if you're looking for the variance or the MSE, then just square it. And all right. So we can use these values to give us a clue that what we are doing is an unbiased estimation. Okay. So we have some examples in our face-to-face class. But in the meantime, we introduce another term here. We have the sampling distribution. Okay, so sampling distribution, it is a probability distribution that describes the likelihood of obtaining different sample statistics, such as sample size and sample variance. I mean, sample mean and sample variance standard or sample standard deviation. Um, we we obtain those from different multiple random samples of the same size taken from a population. So, in other words, when we are taking a sample, we want to have a balanced representation of the entire population. Okay, so that we can have uh, so that every portion, every member, or every cluster of our population is well represented. Okay, in sample distribution, or when a sample distribution approaches a normal distribution, uh, as the sample size increase, regardless of, or should we say, the sampling distribution, like this, that like what we have here, our sampling distribution from our population will become more and more normal. Okay, will become more and more like normal as the sample size increases. So for example here, if we have a sample size of 10, we can our normal if our sample distribution is already normal, then it will just become more normal. Okay? While the others, as you can see, it will partially become more normal. Okay? It will be closer to being normal. Well, how much more if you increase the size further? So, for example, here, if we have a sample size of 30 for this example, um, for this scenario, then as you can see, then the all our sampling distributions are now becoming more normal. Okay, so that is according to the central limit theorem or the CLT. Right? So right, that is regardless of the shape of the population distribution. And for example, if this is the entire distribution, okay, but if you take a very high, or if you meet the minimum sampling size, then you can be assured that you have as a normal sampling distribution. Okay, that's I would like to emphasize on that. Uh, the rest of our topics apply only to normal sampling distribution. Okay, and we can do that by, of course, having the right amount of sample, or the right sample size. Okay, so how do we do that? First, to for us to be unbiased, we have to choose the right sampling method. Okay. Normally, uh, be, we choose more, or we prefer more the probability type of sampling method, or the probabilistic sampling methods. Okay, wherein our options are simple random sampling, like what we mentioned in the previous module, or stratified sampling, or cluster sampling. So by default, we do that. But for some reasons, if your experiment has something else, then you may choose a non-probabilistic method. Okay, like purposive sampling. So you intentionally chose that person that responded, or um that experiment subject. Okay, or maybe you have a quota sampling or a convenience sampling. Whoever you meet outside, that will be your respondent. So that's convenience. Okay, so usually, it's better to have this one, okay? Probability type of sampling method. Now, when we what do you call that? When we decide on the sample size, we have some tips here. I will not read them one by one. You may take a screenshot in 3, 2, 1. Okay. So, when it comes to sample size, one of my personal, or one of the most commonly advised basis is the Cochrane sample size formula. Okay. There are many versions. There are several versions of this. The simplest one is, I think, this one. Um, because the variables that we need here, or the parameters that we need here are easier to understand for beginners, right? So in this formula, we just need the z-score critical value, which is, um ideally, we choose 95% confidence level. That's why we choose the value 1.96 as the critical value, z-score critical value. Okay. And so at the same time, we also need the estimation, or estimated proportion, and the margin of error, or the MOE. So once we have these things, these three, uh, okay, the Z, the P, and the E. So once we have this, then we plot them in our formula, and we get the minimum s- sample size that we need to make sure that our estimation is unbiased. Okay, that's just one step. Um, we're not yet that sure. We're not yet 100% sure. But one of our first steps to get closer to being an unbiased estimator is um by making sure that we meet the minimum sample size. Okay, because according to the CLT, central limit theorem, the higher the sample size, the more normal your distribution is. Okay, so, well, if our sampling distribution is normal, then we can say that the hypothesis testing and other inferential statistical tests that we do are accurate enough, okay, and can be used to conclude for the entire population. Right. So it says here that Cochran's formula is an example of a finite population correction method for estimating the and calculating the sample size. It is used when the population size is relatively small, and the goal is just to adjust the sample size calculation to account for the finite population. Now, if we don't know the population, we consider that as infinite. Okay, so if it's infinite, then we stop with this formula only. So this one actually, this formula is considering our population to be infinite. So usually it's quite high, right? And we want it to be lessened. Okay, we want to adjust it. And to adjust that, we have another formula for that. So it has a continuation actually. This using our NO or the initial minimum sample size for infinite population, and our known population size. Okay, so we substitute that and we have our adjusted, our lower sample size. Um, okay, so for example, if you computed and you needed, using this formula, you have come up with 100 respondents. Okay, if your sample size is 100, um, is known to be 100, but your population is just 500, then you can substitute that here to have a lower minimum sample size. Okay, so let's say 100, so it becomes 100 over 100 minus 1, that's 99. 99 over 500. So 100 over 1 plus 99 over 500. Okay. So if you compute that, you'll see that it's lower than 100. Okay. So that is now the adjusted sample size based on your finite population size, which is your N. Okay. Um, we're going to have more examples in our handout and of course in our face-to-face discussion. Right. And I might include a link also to the handout. Okay, I'll comment them in I'll include them in the description once I have completed it. Okay, so a little bit of advance or a foreshadowing of our hypothesis testing. So if we have a quite high sample size, if we can do that, if you can, for example, you had your adjusted sample size and there's no problem for you to accomplish that, then you may use the simplest, I think, the simplest statistical test for especially for making comparisons or for knowing whether there is a significant difference between something, then you can use the z-test. Okay, because the z-test is assumed that or the z-test assumes that your distribution is already normal. Okay, but if you are not yet sure that your distribution is normal or it has a bit of difference, or it's almost normal only, then you cannot use the z-test. Instead, you use the t-test, right? So there are parametric um types of t-tests, and we have non-parametric types of t-tests. Those are for smaller than 30. Okay. But sometimes we allow that. We allow that, especially for students. Smaller than 30 is um not advised, but it depends on the project. Okay. It depends on the type of the project, right? But by default, we want to have at least a 30 sample size when we want to use t-test. Okay. So remember, higher sample size z-test, lower sample size t-test. Ideally, not lower than 30. Okay. But ideally, we should follow the value that we got from using the Cochrane's sample size formula. Okay. Aside from this, we actually have other options, but I'm not going to discuss them. I'll just mention that um, just like what we mentioned earlier, the Cochrane sample size formula is being used when the population size is known and relatively small, like 500. That is relatively small. Um, so Cochrane's formula can be attainable, or the sample size resulting or that resulted from using Cochrane's formula is quite attainable. Okay, but if you have a very high population size, then the Levin's formula can be used then. Okay, but this is not the Levin's formula is not quite practical for engineering research. Okay, so normally we have a finite population size only. Okay, but of course it depends on the scenario. Other options we have the Krauger's formula and I think it's called Yamin's formula. It's not Yamanes. Anyway, you can take a screenshot of this slide. Three, two, one. All right. So kindly read. And we proceed to the next part.